Hello, everybody, and welcome to the Cosmos Show, place to be if you're curious about the universe. I'm your host, Dr. Sam, the founder and executive director of Wyoming Stargazing. Please remember that you can chat your questions on Twitch or YouTube, and you can also call in and talk to us directly. The number is 929-205-6099. That's 929-205-6099, and you should be able to find that number and the meeting ID that you need at the very bottom of your screen. So if you look at the very bottom of the streaming screen, you should see the meeting ID that you'll need when you call that number because it goes through Zoom. So, but call us. We'd love to hear from you, ask questions, make comments, etc. This week's show is all about the evolution of galaxies. We're going to talk about how galaxies change over time and how astronomers are discovering that process. Our special guest is Dr. Julia DeMillo, who is the Vice Provost of Global Strategies at Catholic University of America, also an astronomer. And she has teamed up with amateur astronomers to learn about the mergers of galaxies. But before we get to Dr. DeMillo, we're going to introduce our co-stars. So first, the Deputy Director of Education and Public Outreach at the Vera Rubin Observatory, it's Dr. Lauren Corlies.
Hello, good to see you, Sam.
Good to see you too, Lauren. Thanks for being here. Next, PhD candidate in astrophysics from the University of Chicago and host of her own YouTube show, Nora's Guide to the Galaxy, it's Nora Bailey.
Hey everyone, happy to be back.
Glad to have you, Nora. Next, postdoctoral scholar from the Simons Observatory, it's Dr. Nick Galitsky.
Hi, everybody.
Hey, Nick. And last but certainly not least, medical doctor and founder of Orbital Biodesigns, it's Dr. Danny Carroll.
Hey guys, nice to be here.
Great to have you, Danny. All right, so this week it is Lauren's turn to tell us a little bit about what she's been up to in her research. Lauren, we're all yours.
Yeah, great, thank you. And I was super excited to get paired with this theme because galaxy evolution is the topic of my research, which is really great. So if you can go to the next slide. A question is, why in all of space did I think that this was the coolest thing to spend my time thinking about? And this fun graphic really sort of gets at the heart of why I find my research interesting. So when we think about galaxies, we tend to think about the collections of stars that make them up and that we see in all the really pretty pictures. But the question is, where did those stars come from? How were they able to form? And what's happening now that they have formed? And all of that information is all linked to how did the gas in the larger universe be able to concentrate within that galaxy to form those stars? And so there are all these processes that are happening all at the same time in this region around the galaxy. And so there's gas that's flowing in, accreting. You can see it sort of flowing into the disk there. Stars, when they get older and they explode as supernova, generate outflows. So they shove a lot of the gas back out into the space around the galaxy. And there's just gas sort of just hanging out there. And so how all of these processes are working together to help galaxies form and evolve is the center of my research. And so we call this region the circumgalactic medium, or the CGM, because astronomers love nothing like they love an acronym. But for me, what was really cool about this is that all of these really important things are happening all in the same space, but you'll notice that I'm showing you a diagram of this, not a picture of this. So in general, this gas, there's a lot of it there, but it's also very diffuse. It's not dense. And so that makes it very hard to observe. So it's hard to measure with our telescopes. And because we don't have that many observations of it in the simulations that I work in, there's not a lot of ways to tell, like, well, were we simulating this gas correctly or not? And all of that's starting to change now in the last, I don't know, like 5 to 10 years or so. We're taking more observations and the theories are getting better and better. So if you go to the next slide. So on the left, this is an example of one of the simulations that I work with. So you can see in the center, there's this yellow region. That's the galaxy, as we would think of it, where all the stars live. And then all of this colorful gas around it is the gas that's feeding into the galaxy or being expelled by it to form the stars. But what you'll notice is, especially if you look in the grayish regions, there's all these squares. You're like, well, the universe is not shaped in squares. So what's going on there? And it's an artifact of how we actually model the galaxies in the computer simulation. And so that's sort of what I'm showing on the right. In general, we all know space is mostly empty. And so if we have only a few cells there to think about what's happening, it tends to be okay. There's not that much stuff happening. But in the centers of galaxies, stars are forming, they're ejecting, there's all this energy going in and out, a lot of things are happening. And so we want to have more cells there, more resolution. And so we have this scheme where we say, okay, I'm going to pick the areas that I think are interesting and put most of my computing power there, and I'm going to ignore a lot of this other space, or at least care about it a little bit less, which is great if you're thinking about how the stars are forming in the very centers of galaxies. But we're interested now in all of this space around them. And so what you're seeing on the left is that actually, not only are we making predictions that are maybe not wrong, you can just visually see that clearly we're not going to predict something that makes sense if you're actually seeing the cells of the simulation themselves. And so if you go to the next slide, is it?
I think we've got the video queued up now. I think that's what's on there.
Oh, okay. I think they're, okay, sorry, it's hard for me to understand. There it is. Okay. So on the left was this original way that we used to think about and simulate this gas. And what our group did is said, okay, well, what if we just dump more of those cells into the spaces around the galaxy as well, and not just in the very center of it? And what you can see is that this dramatically changes the way that we think about this gas, where it is, how it's moving, where it's going, and all of its different properties. And so what I found really cool about my research was that it was not just the observations that were missing or some physical understanding of the universe that was wrong, but just the underlying tools that we were using to try and make predictions for this needed to be updated because we were asking new questions that we had never asked before with the tools. And so then finally, yeah, if you go to the next slide, I have a movie because this is Galaxy Evolution. And so this is what happens if you take that high resolution, instead of looking at one single portion of the galaxy at one snapshot in time, you can actually ask, how does the galaxy and all of this gas evolve with the universe? And again, this is what you're seeing, is it's this really like chaotic, really complex process that all is going to come together to form one galaxy that looks like the Milky Way. So on the left, what you're seeing is the gas itself. Mostly hydrogen. And on the right, what you're seeing is what we refer to as metallicity, or just anything that isn't hydrogen or helium, mostly coming from stars that are exploding. And so you sort of get this complex interplay of like, where's most of the stuff? Where is it going? And how is this chaotic process all going to work together to form one spiral galaxy? And so this is the part of my research that I get excited about, this interplay of how are we using the simulations to make new predictions, and what are the telescopes telling us that we had never seen before because of the predictions, and that interplay between the two. So that's what I've been working on.
Thanks for sharing.
Yeah.
That is super cool. Applause from Nick there. Any questions from any of the co-stars for Lauren?
Yeah, this is super cool, Lauren. I think it's both amazing and frustrating how so many times in astronomy, and I'm sure in other sciences, we think we can safely ignore something, and then we zoom in on it and we go, actually, oops. So I'm just curious, for like one of these simulations that you just like showed that video, like what sort of computing time are you looking at for doing something like that?
Yeah, that's a good question. I know these ones, we're using a big supercomputer based out of NASA named Pleiades. And so I think we're using something like 500 cores. I forget, we ran these a long time ago, so I'm trying to remember the numbers, but I know it took, 6 months to run a simulation like this from start to finish. And so it's an investment of time for sure, but it's still faster than waiting for the universe.
And hopefully you don't get to the end of the 6 months and then realize there was a bug in your code.
You definitely worry about that. And so we have it often. So what this movie is, it's actually, as the simulation runs, it writes out like what it thinks is happening in all of those cells. And so you can control how often it like does that sort of writing for you. And then we make plots as it goes along. You're like, oh, that doesn't look right. Like something like that box we wanted is somewhere else. Or a lot of times you're like, it's stalled. why is it still thinking? It should be making more progress. And you'll find out it's like, oh, this one cell in the simulation of billions of cells is unhappy and it just needs to wait for it. And so it's this fun sort of detective problem to figure out what's going on.
Super cool. Thanks.
Nick, I saw you light up when the supercomputer Pleiades was mentioned. Do you have some experience with that one?
No, it just seems like a good name for a supercomputer. It's fun. Well, I like
imagine
naming
it's a
computers.
cluster, right? It's a
Yeah, right. That's what I was
cluster.
like.
That's what I was thinking.
Yeah, that seems like way more apt than like strange quark, up quark, down quark. The Pleiades supercomputer. I really like that as well.
And what's fun is my whole research group got really excited because in the movie The Martian, they showed Donald Glover's character and he's like typing away like at the mainframe of a supercomputer and it says NASA Pleiades supercluster. And you're like, oh, yeah, that's my computer. My computer, the one that I use.
I have a question for you, Lauren.
Yeah.
So what is the next step? Like what will be the next, I guess where do you take this next in your research?
Yeah, and so what we're working on is exploring more that interplay that I mentioned between now that we have better simulations, what does that mean for how we interpret the observations that we're taking? So typically the way that we observe this gas is we'll look for something very bright in the background, and then we'll look for light that's missing at specific wavelengths that's associated with this gas. But a lot of assumptions go into that modeling, and so using the computer simulations to challenge those assumptions and to say, is it discrete clumps of really dense things that we think we're observing? Is it the sort of diffuse gas around the galaxy that we think we're observing? And how do we piece all those things together to understand those flows that I mentioned in the beginning? Are we looking more at the inflows? Are we looking more at the outflows? Then trying to get a more complete picture of this space around the galaxy. So it's a combination of us improving our predictions, and we're also just building new technology to better observe this gas as well. So we'll have more options to compare against.
Awesome. Thank you.
Yeah.
Any other questions or comments for Lauren?
I always feel like completely humbled when I hear you all talk about this stuff because I know very little. It's like I've got the medical stuff under control, but when it comes to this specific kind of stuff, I feel like I just am a sponge absorbing all this brilliance from you guys. So thank you.
Definitely goes both ways. So that's what's so
Yeah,
fun about
yeah.
the show.
Without a doubt.
Humans are complicated compared to this. I don't know. Plus,
Agreed. I'm like, it's
simulations
mostly
and-
hydrogen, whatever.
Yeah, exactly. Well, yeah, right. Hydrogen and metals.
Right.
Nice and easy.
That's it. Oh, that's all you need. Some gravity, you're good to go.
And helium.
That's fair. We do care about the helium.
Lauren, I had one question, and it's not directly related to this research that you presented, but I'm remembering it from one of the debates I had with my high school astronomy class that I was teaching last year. We were talking about the early formation of galaxies in the universe and whether or not galaxies formed around supermassive black holes or whether supermassive black holes formed in the first big galaxies. And so I had the students take opposing sides and present some information. It was a fun debate, but clearly it didn't actually get anywhere because as far as I know, we don't really know. I was just curious about that.
Yeah. Yeah, as far as I understand, there's still sort of an open question. And like most things in astronomy, it's probably all the things, right? There's going to be some sort of black holes that are coming from the first stars that we think are really massive, exploding and forming black holes. And I really like this idea of, they call it direct collapse black hole. So you have this sort of galaxy that's forming here, except much earlier on, and it just sort of skips the step of forming stars and all of the gas just immediately funnels in and forms a black hole immediately. And so I think it's some sort of combination of those things. And it's another fun piece about this kind of theory work is you could sort of pick and choose what you're putting in. So we don't have black holes in the simulation, for example, but others really care about that. And so you can test all the different questions that you have and see what sort of universe you create.
Very cool. Thanks for sharing.
Yeah.
Well, Lauren, you mentioned earlier that even waiting 6 months for this simulation was way better than waiting for the universe. And so the Nobel note that we have this week is from Gabrielle Lippmann, who was a physicist from Luxembourg. He lived from 1845 to 1921. Won the Nobel Prize in Physics for an invention of coloring photographs using just the interference phenomena of light without any dyes or pigments. If we can go to that slide, I can show you a picture of one of his. There you go. That's actually, so that picture that he developed there it has no dyes or pigments in it at all. It just uses the interference phenomena of light to color it, which is pretty cool. I was like racking my brain to try to find a Nobel laureate who won the prize for something to do with galactic evolution. I couldn't find one. So Lauren, there you go. That's you have to work towards with
I'll
this.
get right on it.
Yeah. But anyways, I thought his quote was very apt for the process of galactic evolution, which I understand to be a very, very slow process as the universe works sometimes. And his quote for us is, "Life is short and progress is slow." So that's as close as I could get to something related to galactic evolution from a Nobel laureate. So if anybody has any comments about that, please go ahead and share them.
I think I don't know that I agree with him that progress is slow. I think progress is intermittent. It's a bit of a fits and starts type thing. I mean, if you think about kind of early 20th century physics and the revolution that happened in the entire field, I mean, people in their entire lifetime, basically their entire understanding was overturned. So I think progress might be slow sometimes, but sometimes it's really fast. You got to be able to catch that wave.
Yeah, definitely a more like punctuated equilibrium is what seems to like typify advances in science.
Yeah,
Anybody else want to go ahead, Danny.
Sorry. I think the second half of this quote probably does not pertain to the tech boom or like, tech evolution, because we see that now. I know at some point the kind of rule of thumb was that technology doubles, whatever that rough rule of thumb is, every 7 years, but it's definitely faster than that at this point. I'm not actually sure what the current estimate is, but things are just accelerating. It's almost exponential, nowadays. But I guess at his time, it probably was a very different story. So but I agree that life is short, though.
Especially compared to astronomy. It's always fun when you're like, you get so used to, astronomy, like topics and stuff, and you say, oh, this is going to be like a really short process, or this is like a really quick thing. And then someone asks like, oh, well, how long does it take? And you're like, oh, only like 1,000,000 years. It's like, it's not a human time scale.
Like coming out from that experimental angle again, where it's like, we've actually accomplished quite a bit, but it feels like it took forever. So I'm more on the life is short and progress feels slow.
Nice modification. Yeah, I can definitely get behind that as well. Any last thoughts about that? Well, Lauren, thanks again for sharing with us a little bit about what you do. That was super cool, and yeah, we'll look forward to updates.
Yeah, it was fun to share.
All right, well, we're gonna move into virtual stargazing. We connected with our local virtual stargazer, Mike Adler, last week. He recorded some cool shots for us. We're gonna queue up that video for you, and hope you enjoy what Mike is gonna share with us. We'll see you back here in just a little bit. Bye.
Hello, my name is Michael Adler. I'm Vice President of Wyoming Stargazing. I'm also a PhD from MIT from a few years ago. I worked for GE for 30 years, and now I am, among other things, an astrophotographer. And so we're going to look at some pictures that I've taken this evening and some in the past. First thing I'm going to do is show you my observatory. It is a clamshell design type of observatory that allows you to expose, in my case, 3 different telescopes. I can operate them actually simultaneously if I wish. I've never had all 3 going once, but I have done 2. This is the one we're going to use for doing some real-time imaging. And then this is a 12, it's a reflecting type telescope, it's 20 inches, a half a meter in size. This is a 12.5-inch telescope of similar design. And this is my smallest, and we're not going to be using that one, but I've used this very often because for large objects in the sky, you use the telescope with the shortest focal length, so you can encompass more area. Okay, so we're going to, first thing we're going to do now is look at the first object, and I'm going to go to the screen. I've already positioned the telescope in the right place, and so we're going to go to the screen, and just took a picture while I were talking. I just took a picture of M20, which is otherwise more popularly known as the Trifid Nebula, and it's called the Trifid because it has these 3 bands, 1, 2, 3 bands. And these are areas of a lot of star formation that's going on. This is located in the constellation Sagittarius. It's quite low in our summer sky, but it's in the summer Milky Way, and it's actually a very beautiful object. It is about 4,100 light years away, so it's a relatively, as things go in deep space, it's close. And in the just about fills up the field of view of my 20-inch telescope. I'm going to show you what this image looks like. This is in black and white, and it's a short exposure, about 20 seconds. I'm going to show you what this looks like in a 20-hour exposure. You can see so we can see the color. This is what it looks like. It's, as you can see, it's quite beautiful. This is actually true color, so these are actually what the colors in the sky actually look like. This red color, however, is coming from hydrogen gas that is being excited by nearby stars. This blue color is actually starlight that's reflected off of dust in this cloud, and it's as you can see, it's very beautiful. These are the areas where there's a lot of star formation going on, and in fact, there are 30 embryonic stars have been discovered in these bands, as well as 120 newborn stars as well. Yeah, so I think I've pretty much described this object. We're going to now move on to the next object, and I'm going to, first thing I'm going to do here is show you the program that actually controls the telescope, and this is it right here. And and now it is pointing at M20. That's where M20 is in the sky. I'm going to now change its designation to M63, which is a very different type of object. It's actually a galaxy, and I'm going to hit find, and there it is over there. And now I'm going to tell the telescope to go there, and it's slowing. Are you sure you want to do this? Yes, and you can see the yellow dot moving. It is about 10:30 at night on the 20th of July. So here it is moving. I should tell you a little bit about it while it's doing this. This is going to a galaxy. It's called the Sunflower Galaxy. It's known as Messier 63. It's not 4,000 light years away. It is 27 million light years away. It's a whole nother galaxy. It's about the same size as the Milky Way, 100,000 light years. But now we're going to go to the program where I take pictures, and we'll go back to that program and look at a picture I just took of M63. It's hiding here somewhere. There it is. Okay, so this is M63. It's what is called a flocculent galaxy. It doesn't have a really well-defined spiral arms, but they're still, you can still you see the circular shape, but they kind of come and go. They're not as continuous as some of the galaxies. It's as I said, 27 million light years away, which means that the light left this galaxy that we're looking at 27 million years ago. It's about a third of the size of the full moon in the sky. And it's about, and the other interesting feature of this, it is about 13 billion years old, which makes it one of the oldest galaxies in the universe. In other words, it's almost as old as the universe, which is over 14 billion years old. So there's this is a very old galaxy. It's located near the handle of the Big Dipper. And I'm going to now show you what it looks like in a much longer exposure, so you can see the details of it a little more clearly. So this is it in about a 50-hour exposure. Many different pictures all stacked together, and you can see this is also a true color picture. So you can see the blue color is scattered light from the stars. It's scattered by the dust. You can see all these red areas. These red areas are hydrogen emission, and hydrogen emits in the red. So what's going on is hydrogen gas is being excited by nearby stars, and it's emitting in these producing these bright little red areas. These are areas where there's likely to be new stars formed in these spiral arms, these flocculent arms of the galaxy. You can see it's the arms get tighter and tighter as you get towards the center of the galaxy. We can zoom in a little bit more and see some more of the detail of the center of this galaxy. A fair amount of detail in this object that I was able to expose. So we're going to now do our last object that I mentioned this, and it's going to be the moon. So we're going to, I'm going to go back to the control screen, and so here we are pointing at M63. There's Ursa Major, the Big Dipper. Now I'm going to ask it to find the moon. And so I hit find, and it's over here. And I'm not actually going to tell this telescope to go there because I'm not going to use this telescope to take a picture of the moon. The moon is too bright, and and it's quite large. So I need a telescope with a shorter focal length and a different type of camera that I can take a short exposure with. So that's in fact what I've done, and we're going to go to back to an image, the same screen that we were looking at before, where the pictures were being taken. And I'm going to show you this picture of the moon, and here it is. And it's a waxing gibbous moon, which means it's not quite full, and it'll be full later this week. You can see some of the major features on the moon. And I'm going to, rather than talk to this image, I'm going to talk to an image where I've actually processed this image some already, and we'll see a little more detail this way. So I'm going to now go to this, and we'll look. It's actually the same image, but I've stacked about 50 of these pictures to get improved signal to noise. Then I've sharpened it. And so I'm going to show you the detail here in a second, but at least for now, just point out some of the major features here. Here are the big seas that are the Maria that is known as on the moon. These are basalt flows that occurred during the early phase of the moon's existence. This is called the Sea of Showers. This is the Sea of Serenity, the Sea of Tranquility, the Sea of Fertility. And then the other major features that we can see here are these two large craters. This is called the Copernicus crater, and this is the Tycho crater. I'm going to zoom in now and allow you to see some of the detail here. And you can see the detail just comes right out, and you can see an amazing amount of stuff going on. So this is the Tycho crater. It is about 85 kilometers in size, and it's about 4,800 meters deep. So it excavated a lot. And these areas out here are spokes, and they're about 1,500 kilometers in distance away, creating quite a splatter pattern that was created. This is a fairly young crater. It was only about 100 million years old, and that's young in the sense that the moon probably was formed over 4 billion years ago. So it is young for the age of the moon. The Copernicus crater is up here, and again, you can see some nice detail of it. I'll even zoom in some more. You can see some of the features, the mountains in the middle. In fact, this mountain in the middle is about 1 kilometer high. So it's these are fairly large mountains. A whole 1,000 meters high, 3,000 feet high mountains in the middle of this crater. Okay, well, I think that's it for me tonight, and I'd like to thank you for joining me, and we'll be doing this again shortly.
Hello, everybody, and welcome back to the Cosmos Show. We're here with Dr. Giulia De Mello from Catholic American University. She's an astronomer there and has teamed up with some amateur astronomers to do some investigations on galactic mergers. Dr. De Mello, thanks so much for being here.
Well, thank you for the invitation. It's very exciting to be part of this group. So,
excellent.
Yeah.
Well, we're psyched to have you as well. Before we get into the guest spot, I just want to remind everybody that you can call in and ask questions directly. You can also chat your questions in either Twitch or YouTube. The number to call in is 929-205-6099. And if you look down at the bottom of your screens, you should be able to see that number and the meeting ID you'll need to call in. We'd love to hear from you, so give us a call. So Dr. De Mello, the first question I have for you is, what's the one question that you wish that everybody would ask you, but nobody does?
Excellent question. So I think what I would like to hear from everybody is, why is Dr. De Mello working with astrophotographers and amateurs instead of professional astronomers to do this project? It's a very challenging project. So this is the question. Do you want the answer now too, Sam? Yeah.
Yeah, please. Yeah, go for it.
So the answer is, well, it's accessibility and availability. So when you have your own telescope, when you have your own private observatory, you can observe as long as you want. So you don't have any committee that's going to decide if your project deserves time or not. So you can observe as many objects as you want, for as long as you want. So, and this is what I wanted to do with these objects. In order to accomplish the goals for this project, I need a lot of deep data. So here we go. I teamed up with the amateurs, and we have started this project just a few months, actually now about 8 months ago. And it's actually, I keep saying that this is one of the positive sides of the pandemic. So, so it's a result of us being at home that made this project actually work, because we could have more time to do things during the weekends because we were not out there. So here we go. And I hope to show you some fantastic images at the end of my presentation.
Wonderful. Well, we've got some slides up that you shared with us, and so yeah, talk us through them a little bit.
Yeah, so this first one is a little busy, and I put a little bit too many text here. It's just that I wanted to kind of brush up a little bit on galaxy simulation and also the history of galaxy classification and why this project is so cool. So on the top right, we have the famous Hubble tuning fork. So Edwin Hubble did this in the 30s. So this is 1936. It's part of one of his books. I highly recommend you look at this article. It's a long article. It's available online. Just Google it and you'll find it. It's free. and he draws the galaxy and proposes a classification scheme for galaxy morphology. So he goes from ellipticals to spirals, and he even divides the spirals in regular spirals and barred spirals. And then the one that I particularly like is actually the round one in between, that's called the S-zeros. We also call them lenticular galaxies. So if you read The Realm of the Nebulae, Edwin Hubble's article, he talks about the lenticular galaxies being some kind of transition type of galaxy. We don't actually know that Edwin Hubble proposed an evolution between galaxies when he looked at the morphologies. Actually, nothing points towards that. But he does say that this looks like a transition galaxy. It has a disk, but doesn't have arms. So he's kind of a little bit puzzled by them. So in our days, many, almost 100 years afterwards, we have people just like Lauren doing galaxy simulation and trying to predict how galaxies evolve and become, like our own galaxy, or what is the future of our galaxy too. So the lenticular galaxies keep puzzling us when we look at them, especially if we look at them in deep images. So, and this is why this project is about deep images of mergers, or DIM, or I call them DIM. So the Deep Image of Mergers project is investigating the S0 galaxies and trying to see if they are a result of collision or not. So if one can click on that little video there, you can see that is a galaxy simulation that is showing a little galaxy that is colliding with a galaxy that is 10 times larger than the little one. So, and the big one has about 300 billion solar masses. It's a simulation that shows when the little one hits the big one, they both start to kind of vibrate. I like to use a simple concept here. So vibrating towards a center point, and it produces these ripples that we call ripples or shells. So this is a prediction. It's not, we can't really tell for sure that this is how it works in the universe, right? So the way to prove that this is really the way it goes is try to find galaxies that are just like that. Where are the ripples, right? So we have to look for images of galaxies that are very deep, because these ripples will be what's left over from the dwarf galaxy. So it's going to be faint, right? Do we see them? Yes, we do. And I started thinking about this project when I was actually working before with colliding galaxies and trying to understand the environment around galaxies. So there is a nice sample of galaxies that's, we call them the H1 Rogues Gallery. It's by John Hibber and collaborators from 2001. So in blue here, you see actually the H1, or the neutral hydrogen, the gas that is the most abundant in the universe, right? And it's amazing enough, many galaxies, this neutral hydrogen is way outside. And it's already a sign that this galaxy, something is going on there. It's not supposed to be spread out like that in tails or in things around the galaxy, so kind of peculiar shape. So so this gallery of galaxies is an excellent source of samples to investigate strange looking galaxies. So I started asking a friend of mine first that I met in a meeting in Brazil when I'm originally from Brazil. So I went to conferences only with amateurs, and they invited me to be the keynote speaker of that conference. And I met one of the astronomers there, and he has his own telescope and all that. And I said, we could do some work together, because I had just seen very deep images taken by amateurs together with David Martinez Delgado, who's an astronomer from the Canary Islands, from Spain. And he had his images already show all these things around galaxies if you expose really deep images, even with small telescope. We're talking 12, 14, 16 inch. So I told this friend of mine, I said, well, new friend at that point. I told him, let's do something together. And then he said, oh yeah. But many years passed, we never done anything. And then it happened that last year we were in one of the Zoom live meetings, and I kind of pinged him again, and I said, oh, come on, Cristóbal, let's try again. Let's do the mergers with your telescopes. And then he said, you know what, I think at this point I know several astrophotographers that could join us. And that's how it started. So if I go to my next slide. So in my next slide, I show the telescopes I'm talking about. So they are small telescopes. So we even have an 8-inch, but this 8 inches, a fantastic little piece of telescope, because it's in a dark sky in Brazil. And the astrophotographer is one of the best astrophotographers we have in the country. So these are really amazing. It's an amazing team. So here, it's already the team after the first results. So now we have more than 5. Now we have about 14 even people that have contacted us, and only 9 that are actually observing right now with their telescopes. So some are bigger than this right now, but this were the initial ones. So they are distributed in Brazil. The original team is all in Brazil. And now the new team, people have joined the team. We even have people in the Northern Hemisphere. So we have an astronomer in Portugal. He's also one of the best astrophotographers of Portugal, and he really loves these deep images. So I think it's going to be a great collaborator, but he hasn't started observing yet. And we have somebody here in Arizona as well, but he's on vacation right now. So that's not working. So when I told them the project and I showed them the rogues gallery and all that, and they were like, oh, they are too small. Those galaxies are too small for our small telescopes. So I decided to go for a proof of concept object that they all know very well and love, which is Centaurus A. So in my next slide, please. I already have the results of the observations of Centaurus A with the small telescope, and we observed almost 42 hours with these telescopes. So also they're very, the astrophotographers are very good at combining images. We have our own technique to combine the images. We use the luminance filter, which is not a science filter. And I will give at the end of the talk, I'll talk about how it is as a scientist to work with astrophotographers. And then, so we developed this technique of putting the images together, even though they are taken with different telescopes. You have to combine them. It's a piece of art at the end, but it works really well. And this is Centaurus A. Seeing here on the left, the colored image, the RGB image is just for show. We don't use the RGB image for anything. We use the black and white, which is the luminance filter only. And here on the right side, we have an animated GIF where we show them all combined together. So in yellow, we are showing the shells that are seen with the 4-meter telescope in Chile, the CTIO Blanco telescope. So as you know, Centaurus A is only visible in the southern hemisphere. And then in red, I have added the shells that actually the little telescopes also see. So they see all the yellow ones plus many others. So it's an amazing feat just to have this. So they were very happy when they saw that this was possible, because now that thing, oh, they're too small, oh, they're too faint. Now they're like, oh, they are confident. So we start observing more. We have at this point observed 6 galaxies. We're about to finish the 6th, so it takes time. You know, Brazil is not very famous for astronomy because we are a tropical country. So it rains a lot in Brazil. So we don't have a lot of good dark nights and clear nights. And this, we can't have the moon when we're doing this, so it has to be also dark night. So there are lots of things that limit the time that we can get with these telescopes. But in any case, I'm going to show you today 2 images that I haven't shown much. One of them I have shown once, and the other one I have not shown before. So this image, we showed the proof of concept at the American Astronomical Society, and it's the one that the Sky and Telescope magazine has shown as well. And on my next slide, I'm going to show you now, and I really hope you appreciate the beauty of it, because I find it absolutely incredible. And I told Samuel and everybody else before that I'm having a lot of fun with this project. So my next slide, please. All right. So now what you're seeing is NGC 5018. So NGC 5018 is not Centaurus A. Centaurus A is relatively nearby. NGC 5018 is much further out. It's actually about 135 million light years away, or 46 megaparsec. And here on the left is the RGB image combined with the luminance filter. So it's 40 hours of telescope time. So you see all this is also known that this galaxy has the structures outside. It's just now you're seeing it in a super deep image. You can see already that the shells or debris all over the place, right? So on the right side, you see what they say, oh, Duilia makes us destroy the image. So now we take this beautiful image and we make the image that actually shows the debris. Can I go back to NGC 5018? There we go. So NGC 5018 shows you on the right side, you see the debris, and I think especially Lauren will appreciate to see what's left from the dwarf galaxy that probably collided with this galaxy. So you can see on the right, on the right side of the circle, you see some stuff there that is really impressive. So yeah, you don't see that on the RGB image, right? But you do have to process the image to actually bring up the shells and the debris. So it's for the first time that little dwarf galaxy's debris is actually seen on this image. So I find it very, very exciting and very even entertaining, if you will. So it's the image that I never showed before. So it's the next galaxy is NGC 5291. So NGC 5291 is 38 hours of observing time. So we have been, I need to check out how far away. It's 51 megaparsecs away. That is almost like 200 million light years. One thing that I didn't bring on this presentation is the H1, but the H1 is spread this way on this galaxy, so it's like vertical across the galaxy. But what's cool on this one is you'll probably see this little cocoon thingy there. All right, if you Google this galaxy and you put the VLT, the Very Large Telescope, the European telescope in Chile, right, in the Atacama Desert, and it's one of the best telescopes to observe. There's a beautiful image, even a Wikipedia page with that image, where they talk about that little galaxy, and they say it's some kind of unknown what this object is. They are puzzled by it. And they actually use a word that they say that the object, I'm reading here, it's a mysterious young dwarf galaxy. And I tell the VLT, it's not a mysterious young dwarf, it's a little spiral galaxy that's being distorted. Look at my image on the right. So when you go deep, you start seeing things that you don't see only with even if it's an 8-meter telescope, but it's not deep enough. You don't see the structure of the object. So here now you see that little puzzling little cocoon is actually a little spiral that has been distorted by the interaction. And we also see a shell. I don't know if you see, but in between the two galaxies, there is some kind of little pouch like this, and that's a shell, probably product of the collision with another galaxy too. So this image is quite powerful. And I don't know if you guys know, use a lot of WhatsApp in Brazil. WhatsApp is an application that you communicate, it's just like text, SMS, right? And I told them, are you guys sure about this? This looks, something is wrong. I think there is an artifact here, and I think something went wrong when you guys destroy the image. And I was talking about something on the right side of, unfortunately, because I can't point to it, I'm pointing on my own telescope, my own computer. So there is an artifact there that I thought it was an artifact, but it's not, because when we look at the VLT image, actually it shows on the VLT image, and it's just a stellar cluster. So it's just, you can see a distorted stellar cluster that is probably born outside there out of the debris of the interaction. So it's really, really amazing, the power of this little telescope. So yeah, it's fun, and it's you see a lot of features that you don't see if you go shallow. You go big, but you go shallow. You can go small, but go deep. Then you can see a lot of things. So the big and the small is the size of the telescope, right? So anyway, what's next with this part of the project is really to continue observing. We plan to publish an atlas of all these objects that we're observing. We have a dozen in the north as well that we will start pretty soon. For now, we're only doing in the south. We have about 20 in the south and a dozen in the north. And the reason we want to publish this is also to help people just like Lauren that do the galaxy simulation, that they can actually see features that appear in simulation that actually are seen in the real universe, not just in the computer universe. On my last few minutes, if I may, I would like just to mention briefly the project that I run in Brazil. That is, so if I can go to my next slide, please. It's a project that I've been doing in the past, since 2016. It's called The Woman of the Stars. And it's to inspire children, in particular young girls, to study science and to see if they would like to have a career in science. So I go to Brazil quite often to give talks, and I go to public schools, and I go to, even in this image on the left, I am in a basketball arena in Sao Paulo with 5,000 high schoolers. So it was an experience of a lifetime. You know, you enter this basketball arena and you say, hi, hello, I'm Julia, I'm an astrophysicist. And they all like, yeah. I said, oh my gosh, I never thought I would be cheered because I was an astrophysicist. So it's quite rewarding. And I see the impact of the project. I wrote a book in 2009 and already seen a lot of young scientists that are, read the book when they were children or when they were teens. And now they're, taking their PhDs, or they're just about to finish their PhDs. And it's really rewarding to see that sometimes all they need is a role model, or somebody that they can get inspired, and it can tell them that if this is what you want to do, go ahead and do it. So that's the other side of my life. By doing this project with astrophotographers, I also want to bring science into the people's home. So, and that's the idea, when you do astrophotography, you can go one step beyond it, and also do science and bring science to the living room. So that's my goal as well. So it's been great. So I'll finish now. Thank you.
Thank you, Dr. DeMello. That was super exciting. And I think the fact that you were in a basketball stadium like that and got applause for being an astrophysicist is pretty awesome. I can't say that I've ever got anything like that. Maybe some of the co-stars have had an experience like that. I certainly haven't. That's pretty cool. Yeah, and if any of those,
I recommend. It's fun.
If any of those 5,000 young women want a job, being a stargazing leader in Jackson, just send them our direction.
I'll do that.
Yeah, and if they need some inspiration, there are 3 co-stars every 2 weeks here that they can get inspired to become doctors and astrophysicists by here.
Definitely.
Well, any questions from the co-stars for Dr. DeMello?
I had a question. So yeah, it's really great to see all the really dim things that you're seeing around all these galaxies, because a big problem that we have a lot is that in the simulations, you make a prediction, oh, we think these sorts of galaxies should exist, they'll have this signature, but we're never going to be able to find them. And so what I was wondering is, there, of the observations that you've made, is there a certain kind of murder that you see that you're finding, or that we wouldn't have been able to see before? Like, what sorts of, are there pieces that we're missing that you seem to be finding regularly? Or is it really just like, oh, this one's totally unique, or this one's really unique?
No, I think what we are finding regularly are these shells. So we do see them quite often, and it's just a question of integrating long time to see it. So because they're faint, so this is actually a great comparison with the simulations, because the simulations predict them. What we also see a lot are the tidal tails, also the result of the gravitational pull, right? So we see that. And in another project that I had that I called the blue blobs, I don't know if you ever heard of my blue blobs, were famous at some point. So the blue blobs were detected first in the ultraviolet, and they are inside those tidal tails. They are H1 tidal tails. So these H1 tidal tails are really rich. Not many people work with them. I highly recommend people to look more at them. So you look at the H1 tidal tails and you find ultraviolet blobs, and then you use bigger telescopes to see what the blobs are. The blobs are stellar clusters, or sometimes small little dwarf galaxies. So they're not necessarily tidal galaxies, because they are not inside the optical light of the galaxy. Tidal galaxies tend to be inside the arm or the pool of the arm. This is inside the H1 gas only. So we see this quite often in all these images. We see these stellar clusters left in the middle of nowhere. So these intergalactic stellar clusters seem to be very common. And this is something that not many people have been working on, and I think they have a huge impact on the metallicity of the universe, because they will blow up a supernova. So, you know, they're ultraviolet source, so they have massive stars, and they are probably responsible for the enrichment of the intergalactic medium, you know, and the chemical evolution of the universe. We can't do much work on that with using spectroscopy because they're faint. So that's the problem. So like right now I have all these deep images, but I cannot even dream of taking a spectroscopy of those because they are just too faint.
Oh,
go ahead.
sorry, I have a thunderstorm starting here. I just had a question. I was curious, I guess, with you're working with these amateur astronomers to get this data and many hours of observations. So I'm just a little curious, like how you recruited them, I guess, and like what's keeping them interested in doing this project that seems like quite a lot of time and effort on their part.
Yeah, so they totally love this. So we meet at least once a month on Sundays and via Zoom. I met them through one that I knew, and then we put, you know, it's just that I'm well known in Brazil as an astronomer. So when people, you know, I have my NASA connection, my Hubble connection, so they kind of know my name, and nobody's called Willia, so they actually do know my name. So it helps to have a different name. This kind of makes them curious, right? Because all you need is this, what triggered their curiosity, right? Because curiosity, you know, drives us, right? Drives everybody and drives the astrophotographers too. So when I bring them this possibility of finding things that they wouldn't dare to even think that their telescopes could find, it's like, really? And then when they find it, it becomes super, super excited. So what happened is I presented it at the American Astronomical Society in January, and I was selected, the project was selected for a press release. And I did a press release, and of course I was competing with all the crazy things that was happening in politics that day. But afterwards, Sky and Telescope came to me and did this interview, and then a lot of other amateurs came to me after that, and we opened. So we have a Facebook page, and we have a form that people fill out, you know, and then we look at the type of telescopes that they have, the type of experience that they have, because you cannot be an inexperienced amateur, because you have to be experienced to do this type of work. So we have a Zoom call with the person who wants to join the team, and then that's it. Go observe. And they have all the instructions to put together the images. We bought a Google Drive where they put all the data. So it's exciting.
Really cool.
Well, I think we have a couple telescopes here in Wyoming that we can probably contribute to your efforts. So we should definitely chat about that and get them online as well.
That would be awesome.
Yeah, we'll make it happen. Dr. Carroll, I think you just mentioned to me there was some cool happenings in space lately. Do you want to tell us a little bit about that?
Sure, absolutely. I don't know if anybody has heard about this, but you know, alongside the regular Olympics that's been happening on Earth, the crew, or a couple of crews that are actually on the International Space Station right now, decided to do their own little takeoff on that. And so I had sent over a video. I'm not sure if this is the same one. It's like 1:15, and it'll kind of show there actually are two crews. One crew that went up to the ISS via the Soyuz, which is the older school way of getting there, and then the other crew which went up via Dragon, the SpaceX Dragon. And so there were a whole bunch of different events. It was pretty great, but I'll let Sam roll it.
Oh yeah, we've got this 1 minute video queued up. Let's play that and see what they have to share with us.
See, they like to have fun too. It's not all work.
Yeah, that's super cool. It's definitely making me a little jealous.
I'm actually going to save the link.
So who won?
I'm actually not sure. I think they broke it down by individual events. I don't know who won the whole thing.
Oh, okay, that's fair.
My bets
That's
are
true,
on
yeah. Who are the
Soyuz.
judges in that situation?
Yeah.
Yeah, really.
Good question. Ground control.
Dr. DeMello, thank you again for joining us. It's been a pleasure, and we'll definitely chat about getting some more telescopes lined up for your work. I think it's really exciting. I think there have been a number of really cool citizen science projects, particularly in the field of astronomy. So I think yours is fantastic, and I would love to help you out with that. And thanks also to all the co-stars for being here, for our streaming master, Gavin, and everybody else behind the Cosmos show that makes it happen. And especially to all of you who are out there watching us. Thanks so much for joining in this evening, and we will see you again in a couple weeks. So until then, be well, and don't forget to look up. Thanks, everybody.